A perfect geometric shape glows deep in the cosmic void, in the endless chaos of exploding stars and swirling dust. One structure defies all expectation. It is called the Red Rectangle Nebula, a stunning anomaly of gas and dust that forms a seemingly flawless rectangle around a dying star. By the end of this, you will understand how this cosmic masterpiece reshapes our ideas of nature, technology, and our place in the universe. We will uncover the binary stars sculpting this form and the mysterious ladder rungs within it that baffle scientists. What does it feel like to witness perfection born from chaos? That rectangle is not a solid object but a cosmic trick of perspective. The Red Rectangle Nebula is what astronomers call a protoplanetary nebula, a fleeting and beautiful stage in the death of a sun-like star. It sits a staggering 2,300 light-years away in the faint constellation of Monoceros, the unicorn. This entire structure is a vast, three-dimensional hourglass of gas and dust, violently expelled from a pair of aging stars at its heart. We are looking directly down the barrel of this hourglass, seeing the dense walls of its waste, and that specific angle gifts us with the illusion of a perfect geometric shape. Its intense red glow comes primarily from excited hydrogen gas, lit up by the fierce ultraviolet radiation of the dying central star. But peer closer into that red frame and the mystery deepens. Inside the rectangle, arranged with impossible regularity, are a series of horizontal bars like the rungs of a ladder or the subtle crossbeams of an X. These are not artifacts or camera glitches. They are real features spaced at eerily even intervals, and their origin remains one of the nebula's greatest puzzles. This is not a messy cosmic explosion. It is a structure of such precise symmetry that it feels designed, forcing us to question a fundamental belief that nature, left to its own devices, does not create perfect geometry. The heart of this geometric wonder is a pair of stars locked in a final, beautiful dance. Catalogued as HD 44179, this binary system is the brilliant engine behind the entire nebula. The primary star is a post-asymptotic giant branch star, a term that simply means it has passed through one of the most dramatic phases of stellar old age. Having ballooned into a red giant, it has now shed its vast, puffy outer atmosphere into space, leaving behind a searing hot, dense core that is rapidly heating up. This dying star is not alone. It is orbited by a smaller, hotter companion star, and their intimate gravitational waltz is the true artist here. The material ejected from the aging primary does not fly off in a simple, expanding sphere. Instead, it is funneled and shaped by a thick, dense disk of dust and gas that encircles both stars, likely created and maintained by their complex interaction. Think of this disk as a cosmic stencil or a very precise cookie cutter. It forces the outflowing material to escape only above and below the disk, forming two vast, opposing cones of gas that shoot out into space in opposite directions. Our view from Earth is almost perfectly aligned along the axis of these cones. We are looking directly down the tunnel of one of them. The rectangular shape we see is not the outline of a solid object, but the glowing walls of that cone's wide opening, with the central dark band being the shadow of the thick dust disk itself. This precise celestial alignment is the simple yet breathtaking reason we witness a shape of such geometric purity. It is a fleeting alignment in cosmic time, a snapshot of structured chaos that will vanish as the nebula expands and dissipates. So the rectangle is not an illusion of design, but a spectacular illusion of perspective, engineered by fundamental astrophysics. But the true magic lies in the physics of that shape, a phenomenon known as a bipolar outflow. To understand it, picture a garden sprinkler on a hot summer day. Water sprays out in a graceful, rotating fan. Now, imagine if you placed a thick, solid disk directly over the center of that sprinkler, blocking everything except two small holes on the top and bottom. The water would no longer fan out in all directions. Instead, it would be forced into two powerful, narrow jets shooting straight up and straight down. This is essentially what is happening at the heart of the red rectangle. The dying star is the sprinkler, ejecting its atmosphere in all directions, but that dense, dusty disk surrounding the binary system acts as the blocker. It is a cosmic traffic cop, permitting material to escape only along two specific corridors, the star's rotational poles. This creates two immense, hollow cones of superheated gas blasting into the void in perfectly opposite directions. For a clearer image, think of two empty ice cream cones placed tip to tip. The narrow point where they touch is the star system itself. The widening, open ends of the cones are the vast lobes of expanding gas. Our solar system just happens to be positioned with an almost perfect side on view of this structure. We are not looking at the cones from the side, seeing their curved profile. We are looking almost directly down the barrel of one cone, seeing its circular opening from the inside. The glowing walls of that distant cone, traced by excited gas, form the straight lines we perceive as the rectangle's sides. The dark band across its middle is the shadow of the thick central disk, the very structure that sculpted the entire nebula. This alignment is not a cosmic coincidence designed for our viewing pleasure. It is a statistical inevitability given the countless stars in our galaxy. From any random point in space, there will always be a handful of nebulae oriented in just the right way to present such a perfect geometric face. For us, that face belongs to the red rectangle. Its perfection is a gift of perspective, a brief and brilliant alignment where physics and viewpoint conspire to create an image of startling order. Yet the rectangle is merely the frame for an even more intricate masterpiece. Within its glowing borders, the Hubble Space Telescope unveiled a detail so precise it defies belief. A series of luminous, horizontal bars that stretch across the nebula's waist, forming the unmistakable silhouette of an X. These are the ladder rungs, a sequence of concentric rings seen almost edge-on, spaced with an eerie, clockwork regularity. They are not static features but expanding waves of gas and dust like ripples frozen in time. The prevailing theory suggests they are the echoes of a stellar heartbeat. Every few hundred years, the dying central star may have undergone a violent pulse, ejecting a shell of material into space. As the next pulse followed, it would eject another shell, colliding with and compressing the previous one, creating a series of glowing shock fronts. With each subsequent eruption, these shells expanded outward, stacking upon one another to create that stunning ladder pattern we see today. It is a cosmic fossil record, a timeline of the star's final, rhythmic death throes etched into the nebula itself. Another compelling idea points to the gravitational dance of the binary stars themselves. Their orbital motion within the thick dust disk could create regular waves or density ripples in the surrounding material, much like a spoon stirring honey creates concentric circles. These ripples then shape the outflowing gas, imprinting that perfect periodic structure onto the nebula. This rhythmic, geometric pattern is utterly unique in the observed cosmos. While many nebulae show beautiful and complex structures, none display such a clean, repetitive, and almost mechanical symmetry as the red rectangle. It presents a profound puzzle, a natural phenomenon that so perfectly mimics the ordered output of a machine or a mind that it challenges our very intuition about the chaos of deep space. That intense, almost unnatural crimson glow is more than just a color. It is a chemical signature, a neon sign written in the language of atoms and light. The dominant red hue of the nebula comes from a mysterious phenomenon astronomers call extended red emission, a broad, featureless band of red light that defies easy explanation. Unlike the sharp, specific colors emitted by simple gases like hydrogen or oxygen, this is a soft, smeared-out glow. the leading theory points to a cosmic ingredient far more familiar than you might think: complex carbon-based molecules known as polycyclic aromatic hydrocarbons. In simple terms, these are vast networks of carbon and hydrogen atoms arranged in ring-like structures, essentially the building blocks of soot. Billions upon billions of these tiny hydrocarbon flakes coat the dust grains swirling throughout the nebula. When they are bombarded by the fierce ultraviolet radiation pouring from the hot, dying central stars, they do not simply heat up. They absorb that high-energy light and re-emit it at a lower, longer wavelength, a process called photoluminescence. For the materials in the red rectangle, that re-emitted light happens to fall predominantly within the red part of the spectrum. It is as if the entire nebula is filled with microscopic red LEDs, each one powered by starlight. This process transforms the nebula from a simple cloud of gas into a colossal canvas of fluorescent chemistry. But the profound implication is not just in the color it creates. These polycyclic aromatic hydrocarbons are complex organic molecules, the very kinds of carbon-based structures that are fundamental to chemistry as we know it. Their presence in a nebula like this tells us that the raw ingredients for complexity, and perhaps even the precursors to life, are being forged in the violent deaths of stars and spread across the galaxy. This is where cosmic curiosity meets tangible innovation. By studying how these space-borne carbon structures form, absorb light, and interact, scientists are not just solving an astronomical puzzle. They are reading a natural blueprint for advanced materials. The unique properties of these cosmic molecules could inspire the next generation of nanotechnology, from ultra-efficient solar cells that mimic this stellar fluorescence to new forms of carbon-based semiconductors. The red rectangle, in its fiery glow, is not merely a spectacle. It is a natural laboratory, demonstrating how the universe itself engineers complex chemistry on a grand scale, offering clues we are only beginning to decode. This precise alignment grants us a snapshot of cosmic time, a fleeting window into a stellar transformation that began roughly 14,000 years ago. That is the estimated age of the major outflow, the moment the dying star began ejecting its atmosphere in earnest to sculpt the geometry we see today. To understand its place in the stellar life cycle, we must rewind the clock. For billions of years, the central star was much like our own sun, fusing hydrogen in its core. As it aged, it swelled into a red giant, becoming unstable. This is the phase that created the raw material of the nebula. Then, in a relatively brief cosmic event, it shed those outer layers, transitioning into the stage we witness now, a protoplanetary nebula. This is a short-lived, brilliant adolescence before its final form. The future of the red rectangle is written in the fate of its searing hot stellar core. Over the next several thousand years, that exposed core will continue to heat up, bombarding the surrounding gas with even more intense ultraviolet radiation. This will ionize the gas, stripping electrons from atoms and causing the entire structure to glow in vivid, fluorescent colors. The red rectangle will transform into a classic planetary nebula, perhaps resembling the famed Ring Nebula, a luminous halo of multicolored gas. This glorious phase, however, is also temporary. Over tens of thousands of years, the expelled cloud will continue to expand, diluting and drifting apart into the darkness of interstellar space. The central star will gradually cool into a faint, dense white dwarf, a fading ember of its former self. This entire cycle is not just a distant spectacle, it is a vital chapter in the story of our galaxy. By studying this phase, we are essentially watching a preview of our own sun's fate 5 billion years from now. More importantly, we are witnessing the ultimate act of cosmic recycling. The complex carbon molecules, the silicates, and the other heavy elements forged in the star's heart and expelled into the nebula will one day become part of new molecular clouds, new stars, and potentially new planetary systems. The ingredients for future worlds and perhaps future life are being scattered into the void by this beautiful geometric death. Its story as a scientific marvel begins not with a grand visual discovery, but with an invisible whisper. In the early 1970s, astronomers were conducting a pioneering survey of the sky in infrared light, a wavelength invisible to human eyes that reveals the heat of cold, dusty objects. The Air Force Geophysics Laboratory's Sky Survey catalogued a strange, bright infrared source in the constellation Monoceros. It was just a number, a point of unexplained heat in the data. The visual identity of this hotspot remained a mystery until astronomers pointed optical telescopes toward those same coordinates. What they captured on photographic plates was not a star, but a faint, distinctly rectangular smudge of red light. The name was born not from poetry, but from straightforward description, the Red Rectangle. For decades, that was all we had, a blurry geometric curiosity in the eyepiece, a shape without detail, its secrets locked away by distance and atmospheric distortion. Everything changed with a launch from Earth in 1990. The Hubble Space Telescope, freed from the shimmering veil of our atmosphere, turned its flawless eye toward this crimson enigma. The images it returned in the late 90s and early 2000s were nothing short of revelatory. Hubble did not just show a rectangle, it dissected it. The telescope's sharp vision unveiled the intricate ladder rungs, the stunning X structure hidden within the glow, features utterly invisible from the ground. Suddenly, the red rectangle transformed from a simple shape into a complex architectural blueprint. We could see the dark band of the central dust disk with clarity, trace the contours of the bipolar lobes, and study the precise spacing of those mysterious concentric rings. Hubble's data provided the crucial evidence that this was a bipolar nebula viewed pole-on, confirming the theoretical models. It elevated the object from an astronomical oddity to a cosmic icon, a textbook example of structured stellar death. Yet Hubble's optical eye only told part of the story. To truly understand the nebula's composition and the engine at its heart, astronomers had to listen across the entire spectrum of light. Ground-based observatories equipped with powerful infrared detectors peered through the dense dust to study the binary star system itself. Infrared light revealed the temperature and structure of the obscuring disk, mapping the very funnel that shapes the outflow. Meanwhile, spectroscopic instruments, both in space and on mountains, broke the nebula's red light into a rainbow, reading the chemical fingerprints within. This is how we identified the signature of those complex carbon molecules, the polycyclic aromatic hydrocarbons causing the extended red emission. It was a detective story written in wavelengths, where each band of light, from the optical red to the invisible infrared, provided a different piece of the puzzle. The Red Rectangle taught us a fundamental lesson of modern astronomy, that no single view is complete. Only by combining the sharp visuals of space telescopes with the chemical analysis possible from large ground-based instruments could we begin to assemble a coherent portrait of this geometric wonder. Its discovery was not a single moment, but a decades-long conversation between technology and the cosmos, a dialogue that turned a faint red smudge into one of the most instructive and beautiful objects in our galactic sky. This perfect rectangle exists because of a singular cosmic viewpoint. We are not seeing its true three-dimensional form, but a precise projection, a silhouette cast against the dark backdrop of space. The Red Rectangle's flawless geometry is a gift of alignment, a stroke of observational luck on a galactic scale. We are positioned almost perfectly along the central axis of the bipolar outflow, staring directly down the throat of one of those vast, hollow cones. It is the same reason a flashlight beam shining directly at your eyes appears as a perfect circle of light, not the cone shape it truly is. If we could fly a spaceship around the nebula and view it from the side, the illusion would shatter instantly. That crisp rectangle would dissolve, revealing its true nature as an hourglass or a pair of back-to-back wine glasses, a structure of graceful curves, not straight lines. This specific alignment is incredibly rare. For every nebula like this oriented to show us its geometric face, there are thousands more tilted at awkward angles, appearing as messy ovals or asymmetrical blobs to our telescopes. This makes the Red Rectangle a uniquely precious cosmic laboratory. Its perfect frontal view provides an unobstructed, clean look at the processes shaping bipolar nebulae. We can see the symmetry of the outflows, measure the structure of the central dust disk, and study the propagation of those mysterious rings without the distortion of a skewed perspective. It offers a clarity that is exceptionally rare in astronomy. This leads to a deeper, almost philosophical realization. So much of what we understand about the universe is filtered through the lens of our singular viewpoint. We decipher the cosmos from one fixed point in space and time, and sometimes, like with this red rectangle, that specific vantage point reveals an order that is not fundamental but perspectival. It challenges us to ask how many other celestial wonders appear strange or unique simply because of the angle from which we see them. The Red Rectangle teaches us that in science, as in life, separating the true nature of a thing from the accident of our perspective is the first and most crucial step toward genuine understanding. The celestial zoo is filled with breathtaking forms, but none wear geometry like the Red Rectangle. To grasp its true strangeness, we must place it beside its cosmic cousins. Take the Crab Nebula, the turbulent remnant of a supernova explosion witnessed on Earth in the year 1054. Its beauty lies in wild, chaotic filaments, twisted and braided by a furious pulsar at its heart. It is a storm of light, a masterpiece of cosmic violence with no straight lines in sight. Then there is the Ring Nebula in Lyra, an icon of stellar death. It presents a near-perfect smoke ring sphere of glowing gas, the classic shape of a planetary nebula viewed face-on. Its symmetry is radial, expanding evenly in all directions from a single dying star, creating a soft circular halo. Both are stunning, but their forms speak to different kinds of celestial endings, one violent and disordered, the other serene and spherical. The Red Rectangle belongs to a third family, the bipolar nebulae, shaped not by one star but by the intricate dance of two. Yet even among these, it stands apart. Look at the Twin Jet Nebula, known as M2-9. It is often called the Butterfly Nebula for its two magnificent curving wings of gas. It is undeniably bipolar, with material funneled into two opposing flows. But its wings are billowing and organic, shaped like flowing silk, not crisp right angles. So why is our rectangle so sharp, so unnervingly precise? The secret likely lies in the exceptional stability and density of its central engine. The binary stars at the heart of the Red Rectangle are thought to be encircled by an extraordinarily thick, massive disk of dust. This disk acts as a far more rigid and precise nozzle than the disks found in nebulae like the Twin Jet. It does not just guide the outflow, it collimates it, forcing the escaping gas into a remarkably straight-edged conical beam with minimal wavering or instability over vast distances. Think of the difference between a garden hose with a precise spray nozzle and one that is kinked and flailing. The Red Rectangle has the cosmic equivalent of a perfectly engineered nozzle. Furthermore, our perfect viewing angle is a gift of cosmic alignment that other nebulae do not offer in the same way. We see the Ring Nebula as a ring because we are looking at a spherical shell from the outside. We see the Twin Jet's wings from the side, admiring their curves. But with the Red Rectangle, we have won the observational lottery, peering directly down the axis of its most geometrically pure feature. This combination of a stable, collimating disk and a perfect line of sight creates a celestial specimen of unmatched clarity. It is not merely a different shape, it is a different category of evidence. While the crab shows us chaos and the ring shows us symmetry, the Red Rectangle shows us structure. It demonstrates how specific, stable conditions in a binary star system can impose near mathematical order on the inherently messy process of stellar death. This makes it more than just a beautiful accident. It is a reference model, a pristine example that helps astronomers decode the fuzzier, more tilted bipolars they find elsewhere. In the vast menagerie of cosmic forms, it is the one that looks most like a blueprint, a ghostly diagram drawn in the red light of dying suns. The sharp lines of the red rectangle reveal a profound cosmic truth that stellar partnerships are the true architects of complexity. While our sun travels alone, this is the exception, not the rule. Most stars in the Milky Way are born in pairs or small families, gravitationally bound in an endless dance. These binary relationships are not mere celestial companionship. They are fundamental engines that drive the universe's most spectacular transformations. The gentle gravitational tug between two stars can funnel dying gas into geometric perfection, as we see in our red masterpiece. But the influence of these duos extends far beyond shaping beautiful nebulae. Their interactions are responsible for some of the most violent and energetic events we can observe. Consider a specific type of stellar explosion, a Type 1, a supernova. This occurs in a binary system where a dense white dwarf star steals material from its companion. When the white dwarf gains too much mass, it crosses a critical threshold and detonates in a thermonuclear blast so uniform and brilliant that astronomers use these explosions as cosmic measuring sticks to gauge the expansion of the entire universe. Without binary stars, we would lack these critical mileposts in deep space. The drama continues when both stars in a pair are massive. If one explodes as a supernova, it can leave behind an ultra-dense neutron star or a black hole. This remnant and its surviving partner then engage in an even more extreme dance, often spiraling inward over eons. Their final merger, a collision of black holes or neutron stars, sends ripples through the very fabric of spacetime itself, ripples we now detect as gravitational waves. Every single gravitational wave signal observed by observatories like LIGO has come from the death spiral of binary systems. This means the red rectangle is more than a pretty shape. It is a quiet, early chapter in a story that can end with the universe itself ringing like a bell. By studying its gentle, structured outflow, we gain insight into the same dynamical processes that, in more extreme systems, forge the exotic objects that allow us to listen to the cosmos in an entirely new way. Understanding the choreography of stellar duets is therefore not a niche interest. It is essential to mapping the hidden architecture of reality, from the birth of geometric nebulae to the distant tremors that confirm our most radical theories of gravity. The same carbon molecules that paint the nebula crimson could one day power our world. Those polycyclic aromatic hydrocarbons drifting in the stellar wind are not just space soot, they are intricate molecular architectures, each one a tiny, stable network of carbon rings. On Earth, we strain to build similar structures in labs, seeking materials with remarkable properties, strength, lightness, and electrical conductivity. But the universe has been running this synthesis experiment for billions of years, in the extreme environments around dying stars. By decoding the natural recipe written in the light of the red rectangle, scientists are learning how to grow better carbon nanomaterials here at home. The process in the nebula is a form of bottom-up assembly where simple carbon compounds energized by starlight link together into larger, more complex sheets and cages. This cosmic workshop suggests pathways to create graphene, the miracle material that is a single atom thick, or carbon nanotubes, which are stronger than steel with less waste and more precision. Imagine a future where we don't just mine materials, we cultivate them, using stellar chemistry as our guide. Laboratories could use controlled energy fields to mimic the ultraviolet radiation near a star, coaxing carbon atoms to self-assemble into perfect lattices for next-generation electronics. These space-inspired materials might lead to ultra-efficient, flexible solar panels that capture light as effectively as the nebula's dust glows red, or medical implants that seamlessly integrate with the human body because their carbon structure is fundamentally organic. The implications stretch into our daily lives. Your future phone's battery could charge in seconds and last for weeks, its components forged from cosmic blueprints. The frame of your vehicle might be woven from carbon fibers engineered from stellar patterns, making it incredibly light and safe. This is where astronomy stops being a distant observation and becomes a direct source of technological inspiration. The Red Rectangle is more than a sight to behold. It is a chemical formula suspended in the void, offering a glimpse of a future where the line between understanding the cosmos and building our world dissolves entirely. The chemistry within this crimson frame whispers a startling possibility that the seeds of life may be born in the graves of stars. Those complex carbon molecules, the polycyclic aromatic hydrocarbons fluorescing in red, are far more than cosmic curiosities. They are, in essence, the same class of organic compounds that scientists find embedded within ancient meteorites that have crashed to Earth. These meteorites, like the famed Murchison meteorite, are time capsules from the early solar system, and they are rich with amino acids and nucleobases, the very letters in the alphabet of life. This suggests a profound connection. The stellar furnaces and outflows of objects like the Red Rectangle could be vast galactic-scale factories, producing these hardy organic molecules and then blasting them out into the surrounding interstellar medium. When a new generation of stars and planets forms from that enriched cloud of gas and dust, those pre-built molecular building blocks are already present, woven into the fabric of infant worlds from the very beginning. Our own early Earth, a sterile rock bombarded by asteroids and comets, was likely seasoned with this cosmic delivery of organic material. The probiotic soup in our planet's first oceans may have had its ingredients pre-measured and supplied by stellar events that happened long before our sun even ignited. This transforms our view of the Red Rectangle from a distant geometric wonder into a potential ancestor. It represents a critical link in a cosmic supply chain, one that takes simple atoms forged in stellar cores and assembles them into the complex structures that can, under the right planetary conditions, spark the processes of biology. If this is a common pathway occurring around countless dying stars throughout the Milky Way, then the galaxy may be quietly, constantly, seeding itself with the potential for life. Every nebula like this one becomes a beacon not just of light but of biological potential. It forces us to ask a monumental question. Is the emergence of life a rare, freak accident on a single lucky planet, or is it an almost inevitable chemical outcome, a natural next step in a universe that seems predisposed to building complexity from stardust? The molecules glowing within the Red Rectangle do not answer that question, but they make the universe feel far more fertile, far more likely to be humming with possibilities we have yet to discover. That crimson geometry has escaped the confines of science to become a modern cultural icon. Its stark, almost digital appearance resonates deeply with our innate desire to find order in the cosmos, making it a perfect symbol for artists and storytellers. You can find its unmistakable silhouette gracing the covers of electronic music albums, where it represents a fusion of natural beauty and synthetic precision, a visual rhythm echoing the music's otherworldly sounds. It has appeared in science fiction art and literature, not as a setting but as a glyph, a mysterious signpost left by ancient intelligence or a natural monument of such perfection it hints at a hidden cosmic architecture. This adoption is no accident. For centuries, humans have looked to the heavens for patterns, from constellations telling epic myths to the orderly orbits of planets suggesting a divine clockmaker. The Red Rectangle fits perfectly into this timeless tradition, but with a modern twist. It is not a pattern we impose on random stars, like connecting dots to form a bear or a hunter. It is a pattern the universe presents to us, fully formed and mathematically crisp, challenging our very definitions of natural and artificial. It feeds the philosophical question that has haunted thinkers since the dawn of reason: is the universe inherently mathematical? When we see a shape this precise glowing in the void, it feels like an answer, a whisper of yes. This drives artists and philosophers alike to use its image as a gateway to bigger ideas about beauty, structure, and our place in a universe that seems capable of drafting its own blueprints. The nebula's influence shows that a scientific discovery is never just about data. When an image this powerful enters our collective consciousness, it becomes a shared language. It gives visual form to our awe, a specific shape to the vast, abstract feeling of cosmic wonder. A musician uses it to evoke a sense of expansive mystery. A graphic designer uses it to suggest flawless, alien technology. A writer uses it as a metaphor for a truth too perfect to be accidental. In this way, the red rectangle performs a vital cultural function. It bridges disciplines. It gives the scientist a stunning object to decode, the artist a powerful symbol to reinterpret, and the public a tangible touchpoint to grasp the profound beauty of deep space. This cross-pollination enriches everyone. Science provides the raw, awe-inspiring reality. Art and culture provide the emotional and narrative framework that allows that reality to resonate within the human heart. The nebula reminds us that our quest to understand the universe is not a cold, clinical exercise. It is a deeply human endeavor, driven by the same sense of wonder that compels an artist to pick up a brush or a composer to write a melody. By studying this geometric wonder, we are not just mapping gas and dust, we are also charting the contours of our own imagination, finding in the distant glow a mirror for our endless search for pattern, meaning, and breathtaking beauty. Our understanding of this crimson masterpiece is far from complete. The next chapter in its story will be written by a new generation of eyes, instruments designed to see what Hubble could not. The James Webb Space Telescope, with its immense gold-coated mirror and suite of infrared instruments, is perfectly poised to become the red rectangle's most intimate biographer. While Hubble gave us its stunning portrait, Webb will perform a deep chemical analysis. Its powerful infrared gaze can pierce through the densest veils of dust surrounding the binary stars, directly sampling the material in the central disk. Webb's spectrographs will break the nebula's light into exquisitely detailed rainbows, reading the chemical fingerprints within with a precision we've never had before. We may finally get a definitive inventory of those complex carbon molecules, identifying not just their presence but their exact structures and how they are distributed. Does the chemistry change from the inner rungs to the outer edges of the rectangle, telling a story of the nebula's evolution? Webb could answer that. It might even detect entirely new types of molecules forming in this unique stellar environment, expanding our library of cosmic organics. Following Webb, the Nancy Grace Roman Space Telescope will bring a different kind of power to the observation. With a field of view 100 times larger than Hubble's, Roman could capture the red rectangle not as an isolated jewel, but in the full context of its galactic neighborhood. This wide-angle view might reveal faint, extended structures or shock waves from the outflow interacting with the interstellar medium, features too large and diffuse for other telescopes to see. It will show us how this geometric wonder fits into the tapestry of its local space. On the ground, the next decade will see telescopes with mirrors the size of buildings, equipped with revolutionary adaptive optics systems. These systems use laser guide stars and deformable mirrors to cancel out the blurring effects of Earth's atmosphere in real time, producing space telescope-sharp images from the ground. Imagine a view of the red rectangle where the ladder rungs are not just visible, but resolved into intricate textures where we can see individual knots and filaments within the glowing gas. These ground-based giants, combined with space observatories, will create a multi-wavelength symphony of data. What new mysteries will this coordinated assault reveal? Perhaps we will see the very mechanism that creates the rungs in action, catching a pulse of material from the star as it shapes a new ring. We might detect the subtle gravitational influence of unseen planets or debris within the central disk. Or we could uncover evidence that the chemistry within this nebula is even more complex and life-relevant than we currently dare to speculate. The Red Rectangle has guarded its secrets for millennia, but the tools now turning toward it are unlike any it has faced before. Its perfect geometry is about to be examined under the most powerful microscope the human species has ever built. That perfect red geometry is a prize reserved for the most patient eyes. While the Red Rectangle's iconic image is a click away online, glimpsing it for yourself through a telescope is a legendary challenge among amateur astronomers. Its faint glow, magnitude 15, places it far beyond the reach of standard backyard telescopes. To even have a chance, an observer needs a large aperture instrument, a dark sky location far from city lights, and a practiced eye at the eyepiece. The reward is not the crisp rectangle of Hubble's portrait, but a tiny, ethereal smudge of reddish-gray light, a whisper of the structure captured in long exposure images. This very elusiveness is part of its magic, transforming it from a picture into a personal conquest, a connection to the cosmos earned through skill and dedication. For most of us, our window to this wonder is the stunning processed imagery shared by both professionals and advanced amateurs. These are not simple snapshots, but digital mosaics built from hours of exposure timed through specialized filters that isolate the light of hydrogen and oxygen, painting the nebula in vivid, false color to reveal its hidden architecture. These breathtaking images circulate through online astronomy communities, on social media, and on resources like NASA's Astronomy Picture of the Day, where the Red Rectangle has been featured, bringing its geometric perfection to millions. This public sharing creates a powerful bridge, turning distant data into a shared object of awe. You can become part of this ongoing discovery without owning a telescope. Citizen science platforms invite everyone to help astronomers sift through mountains of celestial data. Projects like Galaxy Zoo have expanded to let volunteers help classify the shapes and features of nebulae captured in large sky surveys. By spending a few minutes looking at real images and answering simple questions, you contribute directly to scientific research, helping to map the diversity of these cosmic structures. The story of the Red Rectangle, then, is not locked away in an academic journal. It lives in the hushed excitement of an amateur astronomer finally spotting that faint glow, in the shared wonder of a stunning online image, and in the collective effort of thousands of eyes helping science see further. It reminds us that the cosmos belongs to everyone, and every new perspective, whether from a mountaintop observatory or a home computer, adds to our understanding of its beautiful geometric mysteries. Its unnerving perfection inevitably sparks a deeper, more primal question. Could such a flawless geometric shape be a sign of something more than natural forces? This is the great debate the Red Rectangle silently fuels, a conversation that stretches from academic halls to the edges of imagination. The scientific consensus is robust and clear. Every feature we see, from the rectangular outline to the ladder rungs, can be explained through the established physics of binary stars, collimated outflows, and our specific line of sight. Yet the human mind is wired to see intention. When we encounter a shape this precise in the wild chaos of space, a part of us instinctively whispers, "This looks made." It is the same instinct that might make you see a face in a cloud or a figure in the shadows, a cognitive shortcut called pareidolia. The Red Rectangle is cosmic pareidolia on a grand scale, tapping directly into our ancient fascination with symbols and order. In more speculative circles, this has led to ideas of cosmic design or even suggestions of an artifact, a structure built by a civilization of unimaginable scale. These are captivating thoughts, stories that speak to our desire for connection and meaning in a vast universe. but science has a rigorous method for navigating this exact tension between awe and explanation. The process begins not with dismissing the wonder, but by channeling it into a testable question. If this rectangle were designed or artificial, what specific, observable predictions would that make? Would the material be composed of unknown alloys instead of familiar gas and dust? Would the light spectrum show impossible emission lines? Would the structure remain static against the laws of physics, rather than expanding as we observe? The scientific approach meticulously compares these hypothetical predictions against the actual evidence. In the case of the red rectangle, every measurement aligns with natural astrophysical processes. The chemistry is cosmic soot, the dynamics match stellar wind models, and the evolution fits the timeline of a dying star. Finding a natural explanation for something that appears impossibly designed is not a reduction of its magic, it is the ultimate magic trick revealed. It means the universe itself, through the blind mechanical interplay of gravity, light, and matter, can generate a structure of such breathtaking precision that it fools our pattern-seeking brains. This is far more thrilling than any artifact theory. An artifact implies a maker, a single moment of creation. A natural explanation implies that the laws of physics themselves are a kind of silent, perpetual architect, capable of painting perfect rectangles with starfire across the galaxy, anytime the conditions are right. The red rectangle, therefore, becomes a masterclass in scientific thinking. It teaches us to embrace the initial shock of the seemingly impossible, then to dig deeper with curiosity rather than assumption. The answer we find, woven from stardust and orbital mechanics, does not diminish the nebula's majesty. It elevates it, transforming a mysterious red shape into a profound testament to the elegant, self-organizing power of nature. Theories about its perfect form are not just tested with telescopes, but forged inside digital universes. To truly understand the red rectangle, astrophysicists must build it themselves, atom by virtual atom, inside some of the world's most powerful supercomputers. This is the realm of three-dimensional hydrodynamic simulations, where raw computing power meets cosmic artistry. Scientists begin by defining the initial conditions, the digital ingredients of their model. They program in the masses of the two central stars, their orbital dance, the density and temperature of the surrounding gas, and the properties of the thick dust disk. Then they set the laws of physics in motion and let the simulation run. Gravity pulls, radiation pushes, gas expands and collides, all governed by millions of lines of code solving complex equations in a virtual space. These are not simple animations, they are rigorous computational experiments. The goal is to start with a plausible stellar system and see if, over simulated thousands of years, it naturally evolves into something that looks exactly like the Hubble images on our screens. The visualizations that emerge from these number-crunching marathons are breathtaking. Swirling clouds of color resolve into two elegant cones of outflowing material. A dark band forms at the center, exactly where the dust disk should be. Researchers can then virtually fly around their creation, examining it from every angle. They can tweak a single variable, like the orbital period of the binary stars or the viscosity of the disk, and watch how the entire geometry changes. Does a faster orbit create a wider or narrower rectangle? Does a more rigid disk produce sharper edges? These simulations become a laboratory for testing every hypothesis about the ladder rungs. One team might model the stellar pulse theory, injecting a burst of material from the central star every few hundred simulated years. They watch as each new shell expands, collides with the previous one, and creates a glowing shock front that propagates outward, stacking into those distinctive, evenly spaced bars. Another team might focus on the gravitational density wave model, seeing if the rhythmic tug of the orbiting stars can imprint that perfect periodicity onto the escaping gas. The ultimate success is a simulation that not only matches the rectangle's shape, but also its chemical glow, predicting where those complex carbon molecules should form and fluoresce in red. This computational dance is where 21st century astronomy truly lives. It bridges the gap between a single beautiful snapshot and the dynamic, chaotic processes that created it. By building the Red Rectangle in silicon, scientists are not just confirming how it formed, they are discovering the universal rules that might shape countless other hidden wonders across the galaxy, rules written not in stone but in stardust and code. The universe has already engineered the perfect nozzle. That dense disk around the binary stars, collimating the stellar wind into razor-sharp cones, is a masterclass in natural precision engineering. It operates on the same fundamental principle as the nozzle on a rocket engine or the focusing lens of a laser, directing chaotic energy into a controlled, high-velocity stream. For human engineers, this presents a fascinating blueprint. Our attempts to create stable, efficient plasma jets for next-generation propulsion or fusion reactors are often plagued by instability, the plasma wavering and dissipating. Yet, in the Red Rectangle, we see a system that has maintained a stunningly stable collimated outflow for thousands of years, using nothing but gravity, magnetic fields, and a disk of dust. By decoding the specific conditions within that disk, how its density and rotation dampen turbulence, we might uncover new strategies to tame plasma here on Earth, leading to spacecraft engines that are far more powerful and efficient. This cosmic example also whispers secrets to optical designers. The way the dust and gas in the nebula scatter and fluoresce under starlight is a natural phenomenon of light manipulation. Understanding this intricate dance could inspire novel coatings or materials for lenses and solar concentrators, designed to capture and redirect light with unprecedented efficiency. The greater lesson is one of perspective. We often think of technology as something we invent in isolation, but the cosmos has been running research and development experiments for billions of years, stress-testing materials and processes under extremes we can scarcely replicate. The Red Rectangle is one such experiment, a natural demonstration of how to achieve perfect geometric order from chaotic forces. Instead of seeing a distant nebula, we can choose to see a prototype. It invites us to ask what other solutions to our engineering challenges are already written into the fabric of space, waiting in the light of a dying star to be read. That perfect rectangle we see today is a gift with an expiration date. Our cosmic vantage point is not fixed, and neither is the nebula itself. The entire system, stars and glowing gas alike, is sailing through the galaxy, while our own solar system moves on its own separate path. Over millennia, this slow celestial drift will ever so slightly alter the angle from which we view the outflow. The crisp 90-degree corners will begin to soften, the straight lines bowing into gentle curves. The stark X of ladder rungs will blur and tilt, losing its geometric clarity. For alien astronomers in a distant star system, or for our own far future descendants, the Red Rectangle may not be a rectangle at all. It could appear as a tilted oval, a faint hourglass, or simply another asymmetrical smudge of crimson light in a telescope. This transformation will unfold on a timescale utterly foreign to human experience, over tens of thousands of years, a slow-motion reveal of the nebula's true three-dimensional shape. The illusion of perfection is a fleeting alignment in a moving universe, a snapshot of geometry that exists only for a cosmic moment. This temporal perspective adds a profound, almost melancholic beauty to the scientific story. It reminds us that the wonders we catalogue are not eternal monuments, but dynamic events caught in mid-stride. The universe is a gallery of changing forms, and we are privileged to walk through it at just the right instant to witness this particular masterpiece head-on. Our understanding is forever anchored to a specific coordinate in space and time, a single frame in an epic film that has been playing for billions of years. The Red Rectangle teaches us to cherish the view we have, not as the definitive truth of the object, but as a beautiful, temporary chapter in its long and evolving life. Its true nature is painted in wavelengths our eyes can never see. To move beyond the stunning optical portrait, astronomers must listen to the nebula's hidden song, a symphony of heat and molecular whispers. This is where telescopes like the Spitzer Space Telescope transformed our understanding. Spitzer, an infrared observatory, did not see the red glow of hydrogen. Instead, it perceived the gentle thermal warmth of the dust itself. In its view, the red rectangle blazed with the heat signature of the thick, torus-shaped disk surrounding the central stars. That dark band cutting across the middle of the visible rectangle, in infrared light, it glowed brilliantly, revealing itself as the true powerhouse of the structure, a dense reservoir of warm silicate and carbon grains. This was the first clear thermal map of the very nozzle shaping the outflow. Spitzer's data showed how the dust temperature changed from the hot inner regions near the stars to the cooler outer edges of the disk, providing a blueprint of the engine's mechanics. But the story grows richer and colder still. When astronomers point massive radio telescopes like the Atacama Large Millimeter Array toward this region, they detect an entirely different signal. Radio waves pierce through even the densest dust, sensing the faint, specific vibrations of molecules tumbling in the frigid outer reaches of the nebula. Each type of molecule, carbon monoxide, hydrogen cyanide, or even more complex organics, emits a unique radio fingerprint at a precise frequency. By tuning into these frequencies, astronomers can map the distribution, temperature, and velocity of the nebula's coolest, densest gas. They can trace how material flows from the disk into the bipolar lobes, measure the expansion speed of the structure, and even hunt for the molecular precursors to those glowing carbon flakes. This multi-wavelength approach is the cornerstone of modern astronomy, akin to diagnosing a patient with more than just a visual exam. A doctor uses X-rays to see bones, an MRI to image soft tissue, and a stethoscope to listen to the heart. In the same way, the visible light shows us the glowing anatomy, the infrared reveals the warm skeleton of dust, and the radio observations let us listen to the chemistry and dynamics of the cold blood pumping through the system. Only by combining all these senses can we construct a complete, three-dimensional model of the nebula's physics and life cycle. The upcoming James Webb Space Telescope is the ultimate instrument for this synthesis. Its powerful infrared eyes will deliver a chemical map of staggering detail, potentially watching complex molecules form in real time within that sculpting disk. It will connect the dots between the hot star, the warm dust, and the cold molecular gas, turning this geometric wonder from a beautiful image into a fully understood cosmic equation. That utilitarian name tells its own story of discovery. The Red Rectangle was not christened by poets gazing at the heavens, but by astronomers cataloging points of light. Its designation comes from two simple observational facts recorded on early photographic plates: its dominant color and its startling shape. In the grand tradition of scientific discovery, the profound often arrives with a profoundly plain label. This stands in stark contrast to the celestial tapestry above it, woven with names from ancient myth. The constellation that hosts it, Monoceros, is the unicorn, a creature of pure fantasy. The bright stars we navigate by bear the names of heroes and gods: Orion, Hercules, Cassiopeia. For millennia, humans have projected their stories onto the stars, using them as a canvas for our fears, our legends, and our understanding of the world. The Red Rectangle represents a different era, one where the universe is revealed not through stories, but through data, where a number in a survey log or a descriptive phrase becomes the official title. This leads to a charming debate. Does an object of such geometric perfection and deep mystery deserve a more evocative name? Should it be something like the Crimson Loom or the Stellar X? The official answer lies with the International Astronomical Union, the global body responsible for celestial nomenclature. Their process is deliberately conservative, prioritizing clarity and precision over poetry. A name like the Red Rectangle is instantly recognizable and unambiguous to every astronomer on the planet, which is its primary purpose. Yet, the longing for a more mythical name speaks to a very human impulse. We want the language we use for the cosmos to match the awe it inspires. We feel that something this beautiful should be called something beautiful. In the end, perhaps its plain name is perfect. It is a humble label for a humbling object, a reminder that the universe's greatest wonders often reveal themselves first as simple facts, waiting for our science and our stories to catch up. This crimson geometry has been decoded by a truly global conversation. Its secrets were not unlocked by a single observatory or nation, but through a vast international network of minds and instruments. When the Hubble Space Telescope captured its iconic portrait, that image did not sit in a vault. It became a public dataset, downloaded and analyzed by teams from the United States to Germany, from Japan to Australia. Ground-based telescopes in Chile's high deserts provided the crucial infrared spectra, while radio antennae across Europe combined in interferometric arrays to map its cold molecular heart. Theoretical astrophysicists in the Netherlands ran complex hydrodynamic simulations on supercomputers, their digital models informed by observational data gathered from a dozen time zones away. Each published paper, whether from the University of Arizona or the Paris Observatory, became a brick in a shared intellectual structure, building toward a consensus explanation for this perfect shape. This is how modern astronomy works. A cosmic mystery like the Red Rectangle is a puzzle whose pieces are scattered across the electromagnetic spectrum and across the planet. No single country owns the sky, and no single telescope can see all the light. Solving it requires a symphony of perspectives, where a discovery made with a Japanese satellite informs an observation plan for a telescope in Spain, and where a graduate student in India can access the same raw data as a veteran professor in California. This global effort transcends politics and borders, united by a simple, profound question: how does nature create such order? The shared answer, written in the language of binary stars and collimated outflows, belongs to all of humanity. It is a powerful reminder that our quest to understand the cosmos is one of the few truly universal human endeavors, a collaborative project that reminds us we are all, quite literally, made from the same stardust, looking up at the same astonishing sky. The Red Rectangle Nebula is a cosmic lesson in perspective, physics, and profound possibility. It is a natural masterpiece, not an alien artifact sculpted by the intimate gravitational dance of two dying stars. Its perfect geometry is our unique view down the throat of a vast, collimated outflow, a fleeting alignment that reveals the hidden order within stellar chaos. Within its crimson frame, it operates as a chemical laboratory, forging the complex carbon molecules that are the building blocks of future worlds and perhaps future life. It stands as a vital bridge, transforming the death of a sun into the raw ingredients for new beginnings. This single object inspires the engineer with its natural precision, challenges the artist with its stark beauty, and humbles the scientist with its layered mysteries. It proves that the universe is capable of drafting its own flawless blueprints with nothing but starlight and gravity. So the next time you look up at the night sky, remember that hidden in the darkness are wonders that defy our expectations, shapes of impossible perfection born from chaos waiting to be found. Stay curious, for the cosmos is a canvas of breathtaking beauty, and the Red Rectangle is just one brilliant stroke in an infinite masterpiece. But the story does not end with this one crimson shape. We have a question for you. Which idea leaves you more awestruck, that every detail of the Red Rectangle emerges from pure, elegant astrophysics, or that the universe can craft something so flawless it feels deliberately designed? Share your perspective in the comments below. We are genuinely curious to hear what you think. If this journey into structured stardust captivated you, there is so much more to explore. Our channel is filled with deep dives into the beautiful depths of stars, from the intricate rings of planetary nebulae to the upcoming revelations from the James Webb Space Telescope, which will rewrite our understanding of cosmic chemistry. For more explorations that connect futuristic technologies to the wonders of a cosmic lifestyle, be sure to subscribe and hit the notification bell. Our quest to map the heavens is one of humanity's oldest and most noble adventures. Each mystery we solve, like the geometry of this red beacon, lights a path forward, reminding us that we are not just observers of the universe, but active participants in its unfolding story. The Red Rectangle is a testament to the breathtaking order hidden within the chaos, a perfect reminder to always look deeper, because the cosmos still has wonders beyond our wildest imagination waiting to be found.